Hello, my name is Michael Buss. For this supervised learning project, I developed a network intrusion detection model using the CIC-IDS2017 dataset. The scenario for this project is that I'm working as a cybersecurity analyst for a large financial institution. An organization like this may experience millions of network connections every day, so analysts cannot manually inspect every connection. The objective was to build a machine learning model that classifies network traffic as either benign, meaning normal traffic, or malicious, meaning attack traffic. The purpose of the model is to help Security Operations Center analysts identify connections that should receive further investigation. So here we have the problem, the objective, the data set, the setup and configuration, all our imported libraries, everything like that. The selected predictors, and then here we see the 16 selected predictors, and then we connect to the data. 8 files, took a long time, hour to get that uploaded. Then we'll move on to data set exploration. So I used the CIC-IDS2017 machine learning CSV dataset from the Canadian Institute for Cybersecurity. It contains normal activity and attacks such as DDoS, port scanning, brute force, bots, web attacks, infiltration, and heartbleed. The 8 supplied files contained a total of 2.8 million network flow records. Because the complete CSV collection was approximately 885 megabytes, I used a reproducible 12% sample from every file. This produced 339,000 loaded records and retained traffic from every collection day. I selected 16 predictors describing network behavior. These included destination port, flow duration, forward and backward packet counts, bytes and packets per second, packet length measurements, TCP flag counts, and active and idle time. The original labels identify specific attack types for modeling. I converted benign to 0 and every attack label to 1, creating the required binary classification target. So we'll move down to exploration and pre-processing. So here we're at data pre-processing. I inspected the data types missing values, infinite values, and duplicate records. Some rate columns contain missing or infinite values, which can occur when a flow duration is 0. I converted all predictors to numeric values and replaced positive and negative infinity with missing values. Missing values were handled with median imputation inside each model pipeline. Median imputation is less sensitive to large outliers than mean imputation. I also removed 36,360 repeated records based on the selected predictors and target label. After this step, 303,328 records remained. The final modeling sample contained 245,830 benign records and 57,498 malicious records. This was approximately 81% benign and 19% malicious. An important design decision was fitting pre-processing only on training data. This prevents information from the validation or test sets from leaking into model training. We'll move down to the train, validation, and test split now. So I divided the clean data into 3 stratified sets, 70% for training, 15% for validation, and 15% for final testing. This gave me 212,328 training records, 45,500 validation records, and 45,500 test records. Stratification preserved the 18.96% malicious traffic rate in each set. The test set was kept unseen during model comparison and threshold selection. This is important because evaluating on training data would not show how well the model handles new traffic. Let's move on to model development and training. I compared two supervised classification models. The first was logistic regression. It provided a fast and interpretable baseline. Its pipeline used median, imputation, and standard scaling. The second was a random forest. A random forest combines many decision trees that learn nonlinear rules from different samples of the records and features. It is well suited suited to network flow data because an attack may be identified through combinations of packet size, timing, rates, ports, and flags. Both models use class weighting to give additional attention to the less common malicious class. Logistic regression trained in approximately 3.7 seconds, and the random forest used 150 trees and trained in approximately 98 seconds. Validation results. Let's move down there. Oh, we're already there. So the random forest clearly outperformed the logistic regression baseline. Logistic regression achieved 82.69% accuracy and 73.28% recall for malicious traffic. At the default threshold of 0.50, random forest achieved a 99.66% accuracy, 99.06% precision, and 99.17% recall, and an F1 score of 99.11. Its validation confusion matrix contained 36,794 correctly identified benign flows and 8,553 correctly detected attacks. It produced 81 false positives and 72 false negatives. Recall is especially important in cybersecurity. A false negative is an actual attack classified as benign, meaning it may not be investigated. Threshold selection. So, the model returns an attack probability, so I also examine threshold between 0.10 and 0.90. A lower threshold detects more attacks but raises more false alerts. A higher threshold reduces false alerts but increases the risk of missing attacks. For this project, I selected a threshold of 0.10 because it provided the highest validation recall while maintaining precision above 80%. This was an intentionally security-focused choice. The threshold is not necessarily permanent. In a real organization, it should be adjusted based on the SOC's risk tolerance and capacity to investigate alerts. Move down to the final test results. I retrain the selected random forest on the combined training and validation data, then evaluate it once on the untouched test set. The final model achieved 98.71% accuracy, 93.77% precision, 99.85% recall, and an F1 score of 96.72%, and an ROC-AUC of 99.98%. Out of the 8,625 actual malicious flows, the model detected 8,612 and missed only 13. It correctly classified 36,303 benign flows but generated 572 false alerts. These results show the reason for examining multiple metrics. The very high recall means almost every attack was detected, but the lower threshold increased the number of benign flows sent for investigation. Move down to feature importance and prediction. So the most influential random forest features were average packet size, packet length, standard deviation, packet length, mean, and destination port. Together, these results suggested that packet size behavior and the service port were important signals for distinguishing attack traffic in this dataset. Feature importance shows model influence, but it should not automatically be interpreted as cause and effect. The prediction demonstration shows how unseen records receive an attack probability and are then classified using the selected threshold. Finally, we move down to limitations and conclusion. The model has several limitations. CIC-IDS2017 was collected in a controlled environment and may not represent all current financial network traffic. The random split also places traffic from the same collection days in different sets, so future day performance could be lower. Some attacks, including infiltration, SQL injection, and Heartbleed, had very few sampled records. Therefore, strong overall malicious recall does not prove that every rare attack type will be detected equally well. Possible improvements include time-based evaluation, hyperparameter tuning, multi-class attack identification, probability calibration, newer training data, and regular retraining to address changing network behavior. In conclusion, the random forest successfully learned to distinguish benign and malicious network flows with very high recall. It could assist SOC analysts by prioritizing suspicious connections, but it should support rather than replace human investigation. Analysts would still combine model alerts with logs, threat intelligence, and organizational context. And then there is a quick results card, which is seen there. But in conclusion, I don't want to read the last quick results card, but there we go. That is it. Thank you.